Good afternoon, everyone. My name is Özgür Çolpan. I will be the moderator of today's webinar, and it's my honor to host Professor Harry Hoster from Duisburg, University of Duisburg-Essen. So today's talk will be on a very quite popular topic. It will be on electrolyzers. So now I will leave you the floor to Harry. So after the talk, you will have a chance for question and for asking questions. So please click the raise button. So I will give you the microphone so you can ask your question at the end. Okay, Harry, floor is yours.
Okay, thanks for the introduction. Let me see if the sharing works. Does it come through?
Yes.
Yeah, perfect. All right, yeah. So it's a great opportunity to give this presentation. I've been to Izmir many times, but it's been a while that I've been there in person. I think the first time I slept on a park bench near your university because we had to catch a bus early in the morning. That was during my backpacker traveling times when we had to catch a bus to Ilijan the next day. So yeah, at the moment I'm working since about 2 years at Duisburg University, also University Duisburg-Essen, and I'm also scientific director of the Hydrogen and Fuel Cell Research Center that you can see here in the background. And I'll give you a bit of a mixture. So since I'm also interested to see where there could be potential collaboration opportunities, I will not only talk about electrolysis, but also about other things that we do. But I'll also put this a bit into a wider context. So a bit of history about myself. So originally I had studied physics, that was in Bonn. And after that, I did a PhD in Munich, and that was related to surface science. And I became an expert in making single crystals with monolayer bimetallic alloys. And I used scanning tunneling microscopy to identify the atom distribution. So when you have this, for instance, is a surface alloy made out of platinum and ruthenium. The dark atoms are platinum and the lighter ones are ruthenium. And we were looking at how the distribution comes together, how the distribution changes when you change the mixture of metals. But most of all, we also looked at the electrocatalytic activity of those model surfaces. And in this case, obviously, it was about oxygen reduction. After the habilitation in Ulm, I then became an associate professor at the Technical University of Munich, and on their behalf, I was scientific director of a big battery car research project in Singapore, which back then at the peak time in 2012 had like 120 people. So that was an interesting time. So we did many things in parallel. So the most visible thing to the press was an electric vehicle that was built from scratch, based on I think a Volkswagen Jetta, but we built our own car body, and in particular we made a fast rechargeable battery pack, and we made sure that it could be operated with the business model of a taxi. But in parallel to that, we also did fundamental research in the field of batteries. And when I moved to the UK, to Lancaster University in 2014, I brought battery research with me, and I was running a research center called Energy Lancaster there. And there I managed to get the battery research in touch with many other disciplines, one of them being data science. And one outcome of that is that we created an insurance company that would work with battery lifetime prediction on the London insurance market. Yeah, and as mentioned, since October 2021, I have the pleasure to be working in Duisburg-Essen. And about that, I'll show you some examples woven into the topic. So, but I go back another 300 million years, having spoken about myself first a bit. So in the upper right corner, you see Mark Twain, and Mark Twain will get back to us on the last slide. But you see what the Ruhr Valley, which is where Duisburg is situated, where it was 300 million years ago, and that plays a key role. So it was on this slightly differently shaped continent. And I'm struggling to see where Turkey is here. It's all it's a slightly different cut. Maybe you were under the sea back then. Not sure. Oh no, you were here. You were in the southeast. Fine. So the continents look different, but what looked different most of all was that the Ruhr Valley was covered with very, very high trees and up to more than 100 meters high because the climate was very different. Maybe that's what we're going back to, who knows? And those big trees, they created us coal, which was an energy vector, meaning it allowed us to transfer concentrated solar power via time and space. And this coal load ship is a bit like a visual of the energy vector. So this is like the brief history of the Ruhr Valley. The lobsters were already around at the time that the coal forests grew. The dinosaurs were not yet around. Meanwhile, the dinosaurs came and went. The lobsters are still around. The dinosaurs left and left the planet to the mammals. The continents reshaped and the mammals reshaped the cities. So from the coal forests, they built up industry in the Ruhr Valley. And this is what we are now stuck with, because the industry, in particular the heavy industry around steel making and iron making, is all based on the history of us having a local coal supply there, which we stopped using already some time ago. Currently, we are importing coal, but still we don't see this as sustainable. If you look at the energy usage map here, the city of Duisburg is really one of the hotspots in Germany. That is less about nightlife than about energy consumption. So this is just one steel mill in Duisburg consumes more than the entire city of Berlin. So that's a big number. At the same time, Duisburg is, in a sense, the center of Europe. People from the neighbor cities might disagree, but that's what is from an objective source here. So we are well connected to we are connected to Istanbul and also then further on to China via the new Silk Road. Directly by rail. We have, and that's actually the most important part, waterways all the way to Rotterdam and Amsterdam and Antwerp. So we are connected to the seaports that are a bit like the main interface for any sorts of goods into the European Union. And yeah, we used to be in Duisburg a net energy exporter, but now we have become an energy importer, and we have to somehow manage that, because if we don't manage to keep or to create a transition from coal-based heavy industry over to a hydrogen-based heavy industry, then there is not really a future of these jobs in the region. So this is a bit the wider political and historical context. The Hydrogen and Fuel Cell Center, ZBT, we have these two buildings and the hydrogen test field here. I'll give you some examples of what we are doing here very soon. We have like 160 full-time employees, plus about 25 student researchers. And we have a mixed funding we have a bit of baseline funding, but we have a lot of industry projects and a lot of collaboration projects where industry is involved. An important unique selling proposition is our neighbor building here on the left-hand side, and this is where on the science side we are currently building some important strategic relationships, because this building has some capabilities in terms of making new materials and nanoparticles in-house that hardly anyone else has at their disposal. So I'll show you an example of that collaboration later. Yeah, if this is a bit our work in pictures. See here, you see spray coating, you see gaskets operated via dispensers. This is a hydrogen refueling station, but one that is open so that people can test their components, fuel cells, of course. But then there are also less obvious things. This is where people can test any materials that they want to operate in a fuel cell context. And we can then test them in this lab and see if certain new materials, certain plastic under conditions of a lot of hydrogen and high temperature is releasing anything that is harmful to fuel cells. And we do that in a double way. We look first, of course, with a mixture of analytic tools in the laboratory, what comes out of the material. But at the same time, we also look what it does to the performance of a fuel cell. And that's actually a quite important cash cow for our work, because many companies who want to qualify their materials for the for fuel cell applications come to us with that. And if you're interested, I mean, this whole strand of research came out of an accidental observation of random noise during a PhD project, and then it became a whole department that is bringing in a lot of money. Yeah, we have a number of different skills. We can make our own bipolar plates, and out of carbon compound materials, we have a big compounding workshop, and we obviously build our own test rigs and complex setups, but we also go into materials research. More often, we get materials from other people and then test it in a proper context so that they can benchmark themselves against state of the art and get performance numbers from us. And it's less so that we go ahead and synthesize new stuff. So we always have to make sure that we are not really a competitor to our clients. Yeah, so that's a bit of the balance that we have to take. In terms of technology readiness levels, we go all the way up from fundamental new materials and very fundamental analytic methods to fuel cell stacks and then to hydrogen infrastructure. And I'll show examples of all of that. So coming a bit again back to the big global picture, this is from a talk that Nathan Lewis is giving since a few decades and updating it. And I like this really to give an idea. Obviously, to you as a more specialist audience, I'm not telling you a lot new things here, but these numbers might also be of interest for you when you talk to wider audiences. So this is about just looking at the average use by of certain devices that we have in our life. So between 1 and 10 watts, we have the portable electronics. In the kilowatt regime, we have anything that makes heat, that can be blow dryers or toasters. Then another factor of 1,000 would then bring us to small airplanes. Another factor of 1,000, and obviously here we're not on the consumption, but on the energy supply side, we would be at 1 gigawatt, and that would be about the nuclear power plant. And then if we look at the planet Earth, so humans on planet Earth currently need about 20,000 times the power of a nuclear power plant. So 20 terawatts is what we are currently consuming, just on average. So this is an interesting one. This is an interesting number to work at. Obviously, this assumes that we can solve all the problems of intermittence and storing energy and all of that. But just to see how we could get the capacity. If you look about, if you then decide, okay, we want to defossilize the global energy system and get these 20 terawatts out of nuclear power, it's an interesting thought experiment. It would mean like, yeah, in maybe 50 years, we would have to build 20,000 nuclear plants. And that means 1 plant per day. And if you then consider that nuclear plants have a 50-year life roundabout, that means yet you have to build 1 of them per day starting now until eternity. So this is an important number to keep in mind. During all the time that I spent in the United Kingdom, there was a lot of discussion about building the next blocks of that was Hisham Point C. Sorry, Hinkley Point C. Hisham was closer to us, and they talked more about it than actually finalizing it. So we are very far away from even building 1 nuclear power plant per year, and building 1 per day globally is a tough one. And the main reason for that is that the single investment into a nuclear power plant is very huge, which makes which affects the bankability. It's not so easy to get the funds together. And the renewable powers there have, or the renewable energies, they have an advantage. I'll come to those numbers. So these are the numbers for wind and solar power capacity from 2010 to 2020. They are increasing. Then the more recent numbers are not, unfortunately, steeply increasing, but they are staying about on this level that they were in 2020. What you can see is that China is dominating the global expansion here of wind capacity. And yeah, they're not having a 50% share of the global solar capacity build up, but they're close to it. So China is consuming a lot of energy, and that's why many in the West like pointing at China, but they're also the ones who are really making it a mass market for green energy. So that's something not to forget. And then if you take these numbers and try and again use these simple 20 terawatts, that means with this pace, it would take us only 83 years, meaning that if we want to do it in 30 years, we would have to get this game up by about a factor of 3 compared to 2020, which seems a bit more doable than rolling out a nuclear power plant every day. So this number 666 is, of course, a human number for those who know that, but it's also the number we have to keep in mind for the annual rollout. So this is again back to the Ruhr Valley. So when you take the old heavy industry and the steel mines, the steel plants, you would need 3,000 wind turbines, and obviously you would then need the wind turbines together with the wind. At the moment, nobody's really relying on that. So all the big steel mills have their own coal-fired power plants on site. But this makes them also interesting places, and I'll get back to that in a moment. The huge amount of energy that we consume and the huge amount of power generation is only possible to distribute across the planet when we have a useful distribution and storage system. So we had the discussion about the dependence on Russian gas here in Germany, which showed us how vulnerable we are in that sense and how much we depend on the gas tanks. And however, there is no way of replacing this with storing electricity. I once did the maths for the United Kingdom. I'm not sure if I have the slide here. Might not be, no. So for the United Kingdom, I once tried to do the maths. If you wanted to heat the United Kingdom electrically and you wanted to do that for just 1 day out of batteries, then a gigafactory would have to work 60 years to make the battery cells for such an energy storage system. So all these arguments that talk about batteries as being so highly efficient, that's all great, but that only helps you if you are actually having the capacities to make these huge amounts of batteries. And we are closer to making large tanks for liquid or gaseous fuels, so hydrogen or even synthetic natural gas out of hydrogen, and ignoring a bit the efficiency. Of course, you have energy losses. That's then the price of having a secure energy supply. If you don't, the safest is to immediately consume what you produce. But if you want to have a buffer, you have to accept that this comes with losses, and then the scalability is the most important part. And the only things that are actually scalable with the methods that we know today would be huge storage tank for things like hydrogen or even easier synthetic natural gas. So that's the thing one has to keep in mind. If you think we're replacing the old system of taking material out of the ground on a geological scale, we will not get away from that. We might have to put it in first. We might then have to fill old caverns with hydrogen or with gas and then take it out again. But you don't get away without having storage opportunities that are at a similar scale as we had the fresh energy out by mining. So this is from a German newspaper, which is a bit raising an alarm that the hydrogen pipeline infrastructure might be way too slow in its development. That's an ongoing discussion. At the moment, there's still the tendency to leave this to private companies. However, we recently also heard voices in our community that point out that we have to look at this like at the highway network. So it is a strategic infrastructure that serves the whole population. And if you leave that only to the private industry, then they might only serve the sweet spots. They might not create the strategically important grids. We have seen those effects when we left the telecommunication system to the free market, which wasn't really the most efficient way of bringing high internet speed everywhere into the country. I'm not sure how well it worked in Turkey, but in Germany, it was certainly an example where a centralized governmental action would have been more efficient. And at the moment, we have that discussion if for the hydrogen infrastructure, it might also be a good idea that at a higher government level, you decide what is the infrastructure that needs to be built and then contract it out into the private industry. So when you then, this already assumes that you have the hydrogen coming in at the seaports. Here, this shows the German seaports. More important than the German seaports are actually the Dutch and Belgian seaports, but this map stops at the German border. Luckily, where we are here in Duisburg, we are very well connected to an existing hydrogen network from the chemical industry, which should make it easy to also extend this. But other regions of Germany are less lucky. For instance, the state of Baden-Württemberg is a bit panicking because you can see if all the hydrogen comes from the north, then there are all these big chemical plants on the way, which will take it all if needed. So there's not much left for the industry in the south of Baden-Württemberg. That's why especially that state is quite interested and quite keen on getting more hydrogen supplies from the south, so coming from totally different directions, so that they can diversify their sources. So how do you get it into the seaports? Yeah, people who don't like the inefficiencies of making other chemicals out of hydrogen, they will have this purist view that liquid hydrogen might be the best. That might work for distances like United Kingdom to Netherlands, something like that, short distances where the blow of hydrogen is manageable. But for longer distances, if we then have Africa or even Australia in the loop, and then the losses of liquid hydrogen due to the blow-off might be too high. The other problem is whenever you talk about building new infrastructure, you really have to make sure that you have your factories lined up who can actually build all of that. And it's at the moment we don't have so many factories that can build ships for liquid hydrogen, whereas there is an existing infrastructure for a fleet to transport ammonia across the planet. And at the moment, it seems as if that would be the thing that we can grow faster. In particular, this comes here, sorry that this is in German, but what this shows is that there is a huge existing market for hydrogen that can easily then also be turned to a market for green hydrogen, which you can do then by regulation, by making the non-green hydrogen burdened with additional taxes. And then you get rid of one part of the chicken egg problem, which is that green hydrogen is, of course, more expensive in the beginning, but you can solve that by making the other more expensive. And then the green hydrogen has an existing market. So when you talk to the big industry bosses, they are not against this as long as it's as a huge pool of companies would be affected by that, and not only in a certain region in the EU. So that needs some kind of global agreement, but then it can be made possible to first feed the existing market for green hydrogen in the chemical industry and in the steel industry. So when you talk about hydrogen as an energy vector, the hydrogen generation at the moment, and I already had that also in the title of the talk, is a bit of the bottleneck. So this seemingly simple process, I'm also having to tell my students why it is so complicated. I'll just tell them, yeah, you can see these bubbles nicely, but they are actually a very inefficient way of mass transport. And also the ohmic losses are high and all of that. So building a proper electrolyzer that has efficient mass transport and efficient electrocatalysis is far from trivial. And you guys certainly know that better than I do. Just to give you an example, what other challenges there are. When you assume that you can take the electrolyzer technology for granted, even if the electrochemical part works, it doesn't mean that you can get the scale up done very quickly. There's one example that I observed from the distance. So just, yeah, this is Cologne, Bonn here in Germany. And I'm currently up here in the north of Düsseldorf, but I actually went to school on the right-hand side of this red-white dotted area. And there is one of the first pilot plants. So if I zoom in, there's a big refinery by Shell Energy, and they have built the first hydrogen electrolyzer coupled to a German refinery here. They had to buy British technology from the company ITM. And yeah, it's here. It's one of the things that you can now visit. And what I observed from the distance, being still in the United Kingdom, obviously I love this company. I visited them 2 or 3 times as well. It took them still a while to get this 10 megawatt electrolyzer running. And we know that strategically 10 megawatt is still a drop in the ocean. So we need to get into the hundreds of megawatt scale. And it took them a while until this thing actually went. And 10 megawatts is something like this. People tell me that the wind turbines by now are more powerful, but the one that we had in the United Kingdom on our university campus had 2.5 megawatts, and well, that was my currency. So I call this a 4 windmill electrolyzer. Whereas if you go to 100, yeah, then you are at 40. But it's still far from being the rollout speed that we need. Yeah, so that's the world's largest electrolyzer produce green hydrogen. Yeah, that's then 24 megawatts. We are still under where we would like to be, and the reasons for that are not only in the electrochemistry. It is very difficult to actually run and build up a plant that runs in a stable way. Happy to discuss about that if you have questions. So the ZPT department structure, they're like the spearheading department is run by Susanne Palecki, and this is where the new materials and the fancy analysis methods are all hosted, which are then offered to the more technical departments down the road. And when it comes to the field of electrolysis, then a lot of burden is on these 4 departments who deal with anything related to electrolysis, from small systems to big ones. So alkaline water electrolysis is actually very old. There were already in 1902 there were 400 industrial alkaline electrolyzers globally, and they were mainly there to supply hydrogen for fertilizers. I guess that the fertilizer aspect came slightly later because you need the Haber-Bosch process for that. I'm not sure if in 1902 that they already did that. Nevertheless, we know how to build big electrolyzers and to make large electrolyzers for industrial purposes. And obviously here you have a great baseline source of electricity. So running this plant is not as challenging as coupling it to a field of solar panels. Interestingly, the reason why many of these are now out of service is because the fossil-based hydrogen became more cost competitive, and then got this green hydrogen out of the market. But this doesn't mean that one cannot do it again. It in particular gives hope that industry might be actually able quite quickly to build these things again. And companies like ThyssenKrupp near us are really on this. They are technically very well established. So the key thing is that they have a diaphragm between the electrodes, so they don't try and separate the gas phases of the 2 electrodes. Which means that they are in the traditional way, you cannot really operate them at a high pressure, which in some modern applications people try and do, because you can then save a bit of energy that you would otherwise apply for the hydrogen compression. Sorry, here's a German remark which I overlooked earlier. So that's the traditional way. It's well established, but it's for pressure and dynamic operation, it depends on whom you asked how well suitable it is. The main selling point for polymer membrane electrolysis, which is usually the kind of stuff that our groups would work on in the labs, when we say electrolysis, then we consider this the future technology, and we achieve the high pressures, and we also claim that we can achieve dynamic operation. And main difference, apart from the whole thing being operated in an acid environment, is of course the presence of a membrane that only lets the protons through. There's also a strategic bottleneck. If you zoom into an electrolyzer, the porous transport layer that has to bring the electrical contact to the catalyst layer, but at the same time has to allow the water in and the bubbles through against the stream of water. That is already an expensive piece, but this is an even more critical part. So the electrocatalyst let me just see if I can become a laser pointer. Yeah, I can. This might be a bit easier to see. So if you then zoom into this region and look at the iridium that you have in the catalyst layer, then there are some interesting numbers to be talked about. So the globally available amount of iridium every year is 7,000 kilograms. And if I was now live in Izmir, I would ask you how large that is. But in this way, I just have to tell you, this is like 70 times 70 times 70 centimeters. So I always say you can easily put that on a table, but the table wouldn't be able to take the weight, but it's really a small volume. And the reason why the dinosaur is here is because dinosaurs have a difficult relation to iridium, because the meteorites that extinguished them brought a lot of iridium to the planet, which is why we know that it happened, because we detected the iridium traces everywhere, and in the same time layer that we attribute with the disappearance of dinosaurs. So, but that also means it might not be a good idea to ask for more iridium if it comes to the planet on the same route. So we have to be economic with the amount of iridium that is available. And there's a few numbers to look at it. So iridium can become the bottleneck in rollout of PEM electrolysis. And there is again, there's a nice paper that gives an overview of the market development. Long story short, here you see annual installation rate in gigawatts per year. You remember that we were earlier rather talking about hundreds of gigawatts per year. So this is already a factor of 100 less ambitious than what one would ideally like to see if one says, okay, I want to have green electricity, but at the same time, I also want a flexible energy storage, which requires to make hydrogen either as storage or as a precursor for other e-fuels. So already in this scenario that is rather conservative, the iridium becomes a bottleneck. And we can try and further reduce the iridium demand. And I'm sure that some in your institute are also doing that. We can look at alternatives. But yeah, all the alternatives that we've seen so far had a lot to do with metals like ruthenium, which are also not so abundant, might be slightly more abundant than platinum, but than iridium. The main issue about the mining of iridium is that it comes as a byproduct. Here you can see it in this diagram from platinum and palladium mining. And you cannot really independently scale up the market for iridium without scaling up the market for platinum and palladium. So there is an issue here. So we have to be good at reducing iridium. We will nevertheless have to start the rollout to maybe get into this regime of gigawatts per year, so that we have the PEM electrolysis industry. But then we have to make sure that this industry is capable of using new materials in a drop-in method. In principle, in lithium-ion batteries, we had a similar scenario. The early market entrance batteries were relying on cobalt oxide-based or lithium cobalt oxide-based cathode materials. And now one of the goals in the battery industry is to really reduce cobalt usage as much as possible. However, the market entry was only possible with the low-hanging fruit, which was accepting cobalt in your mixture, and then that way being able to build batteries that were actually safe to operate and would last a bit. So thinking only sustainable from the very beginning and then not allowing the product onto the market might not always work. But in lithium-ion technology, the key thing was that all the manufacturing was developed, and bringing in new oxides is a drop-in process that then takes a bit shorter to the industry and can be implemented. I think we might hope to do something like that in the electrolysis industry. So we have to start with iridium and then make sure that the industry is capable of making adjustments once we have found better ways of using iridium or even other metals or metal mixtures. The other big player that is in this context is the anion exchange membrane electrolysis, which you're all familiar with. So it claims to combine the advantages of cheap materials, so mainly nickel-based electrode and support materials that you would have in the classic alkaline electrolyzer, and the dynamic operation and the safety that comes with the membrane that would come from the PEM electrolyzer. So this is a bit like how Evonik is selling this technology, so bringing the two advantages together. However, it's not so clear how quickly this will all be ramped up. Nevertheless, we are also involved in the research related to that. Here, I want to give you a bit of an example how we strategically work together with the research institutions and the other universities that are with us in the Ruhr Valley. So we really work along the technology readiness levels. A lot of fundamental research comes from the Max Planck Institute of Chemical Energy Conversion, which was once started by Robert Schlögl, whom you might know, and Ruhr-Universität Bochum. Alfred Ludwig did a lot of systematic materials search and also that brings together the experimental and the computational work. And we have the opportunity of making any new particles then also in larger quantities based on these nanoparticle reactors that we have in our neighbor building. Whereas we are then able to bring new materials at an early stage into a more realistic environment than the classic electrochemical setup, which maybe has a rotating disk and a potential start. So we do the classic rotating disk and we love it, but at the same time, it's also important that any new material is tested under realistic conditions early on. So the main reason to do that is that the stability under operation conditions is often more important than the performance that you would initially see. And so which would mean that a material that is a poor performer in the rotating disk but is stable, does that poor performance over a longer time, might actually win a competition that is taken in a real world environment. So we are splitting the research so that we do the fundamental work and the application oriented work in parallel, and then we can bring that all to the gigawatt scale, which is this tri-campus that I will talk about in a few minutes. Yeah, so that's the collaboration between those two buildings. I think I'll skip that one. Coming to fuel cells and transport. That's interestingly the topic that in the public is most dominating. I think that has to do with cars, and that cars are the main energy converter that everybody's used to at the moment. More recently, also people started talking about heat pumps and all of that, which is the other big energy converter that people have, well, heating the homes and getting around. The heating home part actually goes in the right direction because it already reflects the fact that the amount of energy we need for heating buildings is much, much larger than the amount of energy that we need for transport, even though any new energy vector like batteries or hydrogen is always first about, okay, what does it do in cars? But for cars, it might not be that that important for the years to come. Because I already mentioned that there is an existing market for stationary hydrogen usage in other industries, and the fuel cell car industry is slower than we expected. So here the market was growing in the transport field for fuel cells, but this is still a very small, so a very small scale altogether. So okay, I think this is a German point. So I think this is 1,965 megawatts. But thinking globally, like a market of 2 gigawatts, is still too small. So so talking about the fuel cells, how do we see the fuel cell in the context of transport? We certainly have a market for when it comes to passenger cars. It will be cars that have to be operated in fleets, or for business people that have to go long distances and don't have time for refueling. That might be an early starter market. But at the moment, the most momentum in developing automotive fuel cells are really in the heavy goods and the bus industry. So companies like MAN are really investing heavily into this and want to make sure that they can bring fuel cell propelled trucks on the market early on. The reason for that is that the payload of battery powered trucks isn't that great. So I had always thought initially that given that they are so big in the first place, the big bit of battery shouldn't make such a big difference. But in that case, it actually is down to weight. So the battery would then be way too heavy. And in that case, you reduce the amount of goods that they can transport, and that makes them less attractive to be in batteries. That's why this green fuel cell electric vehicle market will be in this transport related long distance small cars, and in particular buses and trucks for longer distances. Also, trains are an interesting one. So we have the first pilot train line in Germany now running. They are using hydrogen that was otherwise just blown off by a chemical plant, where I think that was from chloralkaline electrolysis, where they didn't have a local use for the hydrogen. So that came in handy, and they then created the local hydrogen refueling stations. But these are accidental matches, so there's not that much unutilized hydrogen available that it will be important on a larger scale once we change the system. But to get a few pilots running, it's very useful. And also for the electrification of train lines that are longer than 80 kilometers and are not yet electrified, then hydrogen is actually a quite good option, because for trains it's quite easy to get the range together. And for longer distances, also the hydrogen is more useful than batteries. Under 80 kilometers, battery powered trains would be the preferred way away from diesel. Important thing in this context is the all diesel powered locomotives already are diesel electric, for those who might not have heard that before. So they are electric anyway, so the diesel is only a generator. So if you replace that diesel generator by a fuel cell, you wouldn't even have to totally redesign the locomotives. For ships and planes, the hydrogen-derived synthetic fuels might be more relevant, because then the density, here in this case, the volumetric density, and in both cases, actually, volumetric density becomes an issue. And I think these e-fuels we will first see there, where alternatives are really very difficult to make happen. Yeah, coming back to ZPT activities and a bit what we do in the fuel cell field. So this laboratory was the first one in this building, and it's now completely empty. So I don't have a current picture here in this talk, but if you would visit us, you wouldn't see anything. So I'll give you the virtual tour, and it shows you a bit how deep we go on this poster into the fuel cell research, and gives you a few examples. And just a very short message. Yeah, we do it everything. We develop flow fields, and we test other people's flow fields and benchmark them against ours. This is a standard fuel cell that we can then easily use to benchmark materials without or materials or designs without violating anyone's IP. Here you see a coated membrane. When it comes to the value chain, there's also an important piece to be noted about fuel cells for cars. The costs related to the catalyst, so to the noble metals, and the ink and all of that, is really more in the order of a quarter. So there are other parts. These are the bipolar plates, BPP. They also contribute a bit, but these two things together, that many people in the fuel cell world would consider the most important things, they are still less than all the other little pieces here. This is not only bad news, because it means that the hydrogen cars or hydrogen propulsion is convenient, because the refueling is fast, and this makes it very attractive for especially also heavy goods applications. But this comes at the price of having a more complex system than a battery and a motor. However, it also means that there's a lot of money to be made for the component supplies industry. So those that were so far making a living of building valves and connectors and sensors for petrol cars, they are still in business if they start to change early enough and make sure that their products also work in the context of fuel cells. And this is also one of our missions that we have as an application-oriented research institution in combination with the fuel cell industry. Looking at our region, we actually found out that the fuel cell industry is not so highly represented in the state of North Rhine-Westphalia, but we have a lot of activities related to hydrogen infrastructure, so making hydrogen refueling stations, operating them, but also electrolysis and electrolysis components. And in particular, back to fuel cells, the context of hydrogen and ships, so especially inland waterway ships, are an important one, because we are. I already mentioned that we are a big hub. So here is I think Europe's biggest seaport, inland port, not seaport, of course, but the biggest inland port, and that comes with its own specificities of infrastructure. And we are now trying to convert this port to be hydrogen ready. We already won the company Plug Power over to the seaport, and we now have the Norwegian company Hydrogen Plus also arrived in Duisburg. They want to recruit up to 30 people here, so we are very exciting. I hope that we will meet them already tomorrow. So the interesting thing is there are these hydrogen-related companies deciding to come to Duisburg, and many hadn't even heard of us before. So we are one of the few hydrogen research centers in Germany, and we seem to be at the right place. So we are still not the reason. We are a nice to have to be here for the new companies that bring hydrogen economy here. So that's good news. So then the last point I want to talk about a bit is about the hydrogen infrastructure, which we do on our hydrogen test field that I've depicted here. So those were the plans that by now have become real. So we had recently had a high visit by Chancellor Olaf Scholz, and she's the president of our parliament, Bärbel Bas, and so we gained quite some public attention here. So what we have here is obviously a hydrogen refueling station, but we also make our own hydrogen. We have a PEM electrolyzer. We earlier also had alkaline and solid oxide electrolyzers here, but after the project stopped, so then we only kept the PEM electrolyzer running. We have obviously a control room. We have hydrogen storage bundles with supplied by local suppliers, so that they can test their storage technology in the context of hydrogen refueling. The main dispenser is this one here that can do hydrogen refueling for cars. And more interesting, we also have a direct air capture source, which is this thing here. So here we provide CO2, or we capture CO2 and lead it into a methanation plant here, so that we can make our own synthetic natural gas, at least at the scale of 10 kilowatt. And so it's a very energy inefficient way of doing things, but we might at some point really have to do direct air capture at whatever places we have nothing else to do with excess energy than just burning turning CO2 into something that we can either use as a fuel, ideally not decentralized, or store it as a solid. Might even be more important. Might happen. Yeah, but it's stuff that we test here on site, and whenever I come here, there's something new, and it has such a high dynamic that it's even impossible to communicate that in the house. I mentioned that earlier, that we test other people's components, and we also test other people's hydrogen purity. And again, we do two things. We measure with classical chemical analytics what kind of impurities are in the hydrogen, but we then also test with fuel cells if that impurity actually is anything the fuel cell cares about. Yeah, so fuel cells are in test rigs here behind the analysis instruments. Yeah, and so we have already qualified 50 hydrogen refueling stations in Europe. This we do together with other partners, mainly ZSW and Ulm and the CEP. And yeah, this is an important business. And it wasn't even so easy to make a way of invent a way of taking samples of hydrogen, bring them home without all the dirt in the hydrogen being absorbed by the walls, which is usually what you have when you try and analyze any kind of gas samples ex situ. Yeah, and then the big next playground is this TRI, the hydrogen proving area, which as of now is supposed to be hosted in this big in this big hall here on the steel plant of Hüttenwerke Krupp-Mannesmann, which is also related to Thyssen. And they have their own coal-fired power plant. They have their own port here, and they also have firefighters on site. So it's the kind of place where you can build a few megawatts in a safe way, where you have the electricity power, and even better, if you make big electrolyzers here, you have a taker for the hydrogen, which is the steel plant is happily taking it all. But if you don't produce hydrogen, which will very often happen with a new plant, then they just do what they always did, and that is actually a great opportunity to host such a thing. So we still have a few issues to solve. And this project here isn't even supposed to be about electrolysis, but it is on the same side. This is about testing large-scale equipment for hydrogen in the context of transport. Yeah, the last thing that we are now inventing is this hydrogen innovation office. So where from all departments we will have consultant people, so some part-time, some moving full-time to consultancy jobs, so that we can also really be an interface to industry, but also to politicians. And that will help us a bit to understand what the needs of certain industries are, but then also to explain things in a proper context, so that politicians don't make rush decisions without feeding things back to us. And that actually works quite well. We were already consulted about new legislation for hydrogen infrastructure, where people from the ministry had just Googled us and came over and discussed the new law drafts with us. And since we have built a lot of hydrogen infrastructure in the past, that was actually a good thing to do, because we could tell them, okay, this paragraph shouldn't actually be applicable in this context because it was made for steam reforming, has nothing to do with hydrogen. So stuff like that we discuss with industry, and I think this is also having a value for hydrogen infrastructure as much as our fundamental research. Yeah, again, this was our 2-hour visit by our chancellor. It was very cool to see how a politician becomes a different person when all cameras are off. Here we had in this yeah, rather colloquial meeting atmosphere for 45 minutes, and he wanted to have some of the questions in advance so that he could prepare himself, but he was very well prepared. He could answer the questions and give also perspective without having to consult any people that were with him. So that was an interesting experience, and shows you that people are behind the energy transition. We also found out that the Ruhr Valley in Germany is one of the leading innovation cluster in terms of hydrogen on the planet, which makes us happy. I wouldn't have thought that we would be listing here in these ranks, because we are still having the burden of a lot of legacy industry, and the whole research aspect and innovation aspect came only over the last few decades. So, but it's even better that we are listed there, because for instance, you don't see Detroit here. Yeah, I would have thought, okay, we could be rather in the Detroit situation than being comparable to Seoul or to Osaka. Okay, so that brings me to the end. I've shown in the beginning this 20 terawatt number means that if we want to fossilize in 30 years and have a lot of hydrogen as an energy vector there, we have to keep the number 666 gigawatt capacity to be added per year in mind. And that means whatever we want to do, we better make sure that we can quickly build big factories, and we might have to leave aside certain efficiency aspects for the moment just to get this new industry going. We have an existing market for green hydrogen, which is very good news. So that means that for the hydrogen, we will not have the same problem that we had with battery cars, that in the beginning everybody talked about we don't have charging station. Here we just have industry. He will take the hydrogen and already is used to doing so. So that's great. And then transport will come in later. And yeah, the hydrogen market will grow before we see a lot of fuel cell cars, but the hydrogen infrastructure must really go quickly. And it's the only chance to keep industry in regions that once started based on coal. So this is a picture I've also taken in Duisburg. This is now a museum. It's a lovely museum, but we don't want the whole industry to be a museum. And the chance to get there is really to follow Mark Twain, to make sure that in the time of a gold rush, you are one of the instances that sell the tools, the pick and shovels, and not try to make hydrogen, because that's not what we will do. We might build demonstrator plants, but we will be the ones who sell the electrolyzers and later on the tools to make the electrolyzers and all the specialized materials. And I think this is the way forward. And then we happily take back the green energy, the green hydrogen that was made with our technology somewhere else on the planet. So that's our master plan for the Ruhr Valley. And that brings me to thank you for your attention.
Thank you, Harry, for this excellent presentation. Actually, I have learned a lot myself, and I didn't know that you had such an advanced research center. So thank you again. So the floor is open for questions, and I think there's one question from the chat. And the question is, do you study system efficiencies of PEM electrolyzers with balance of plant?
Yeah, we do that to some extent. We sometimes get requests like that, but this is exactly the kind of stuff we want to do more in this Hydrogen Innovation Office. The whole balance of plant thing is totally on our radar. One thing we want to look at very carefully, I've shown how we looked at the gas impurities for fuel cells. We want to look at water impurities that come in all these circuits. And that is then looking at the lifetime and how lifetime is affected by the choice of materials that you make on plant level. Yeah, so we try to be very high level there and see where the industry needs us first. But the balance of plant part is certainly something we also do.
Okay, thank you very much. So please click the raise button if you have any questions, then I will give you the microphone. But there's another question from the chat. What type of dryers are used for purification of green hydrogen, and what temperature do we have to cool the produced hydrogen? Also, do we need heating?
So I'm not sure if I got that. To get the water out of the green hydrogen, on the electrolyzer plant.
Well, the question is again, what type of dryers are used for purification, and what temperature do we need to cool the temperature? Or what temperature do we have to cool the produced hydrogen?
Yeah, so those things I'm not familiar with, I'm afraid. So I know that we have purification processes there, but that wouldn't be the kind of stuff I would be directly dealing with. I think this is the things where we would look at other people's solutions and test them in a proper context, but it wouldn't be where we develop methods. So I'm struggling answering that. Sorry.
Okay, are there any other questions? I don't see any hands raised up. Maybe not. Okay, then, okay, one more. Will the recorded webinar will be, yes, it will be available. We will share it. If it is okay with you, Harry.
Yeah, fine. It's fine.
Okay. Okay, then I think there are no other questions. And thank you very much again for this excellent presentation. And we hope that you can also come and visit us in Izmir.
Yeah, it would be great.
So there's a possibility we will also have such a resource center. So maybe I will contact you regarding the equipments in your center soon. We can discuss it. Okay.
Yeah, happy, and also happy to advise when it then comes to how to operate it long term. Yeah, maybe we've been through many hard times, so more than happy to help partners over the planet.
Okay, thank you very much. Okay, so this concludes this webinar. Thank you very much for all of you for your attendance, and hope that we will meet in the next meeting. Okay, have a great day. Take care.
Bye bye, everybody.